project I did, my colleagues and I look at all the aspects of utilizing nuclear energy beyond the conventional electricity generation, essentially making good use of the large amount of heat produced by nuclear plants. When I was preparing these remarks, I started from the amount of hydrogen that would be needed to replace a typical blast furnace of 2.7 million tons per year with direct reduction iron made with hydrogen. And that would require about 150,000 tons of hydrogen per year, or about 5 terawatt-hour of hydrogen. So in order to produce that hydrogen, you would need a plant that's about 1,000 megawatt of capacity, operating at 90% capacity factor, or much more installed capacity would be needed if you operate at a lower capacity factor, such as, for example, with variable renewables. And this is to just replace a single blast furnace, while there are obviously many more around the world. In addition, in order for the iron to be defined as green, the electricity needed for the hydrogen production needs to also be produced without carbon emissions. So where to find this staggering amount of hydrogen is exactly where one of the key issues is for the transition to green and steel, green iron and steel. How can a hydrogen demand of this size be met realistically with no carbon emissions and in a dependable way? This is why we are here today, to discuss solutions for a complex problem that is of vital importance for the future of our planet. So, dear colleagues, I bring good and bad news. The bad news is that it will not be easy to produce the amount of hydrogen needed to fully decarbonize the iron and steel industry with low carbon sources. It will not be easy. The good news is that there are low carbon technologies that are out there and available to help. Nuclear energy is one of them. So a typical large 1,000 megawatt nuclear plant can produce a large amount of hydrogen, about 150,000 tons a year with existing low temperature electrolyzers, which is exactly the 5 terawatt hour a year of hydrogen we mentioned before to replace your typical large blast furnace. That would be carbon free, would be available 24/7, would be dispatchable and secure. But how realistic is the nuclear power option?
Steel is one of the central pillars of our global economy, which will also continue to grow because we need steel for the transformation process itself, for green technologies, for windmills. So the demand for steel, and especially green steel, will grow more and more. But at the same time, everybody knows as well that the steel production is responsible for up to 7 to 9% of the global anthropogenic CO2 emissions. So, and referring to the total industrial CO2 emissions, we talk about 30%. So you see this is a very important point to tackle here the steel industry and to start the decarbonization process here. And the vast majority, as you can see on the slide, of the emissions is caused by the carbon-based integrated steelmaking route. Let me say we pursue a holistic approach that comprises the entire process chain of avoiding CO2 emissions. That means the carbon direct avoidance, CDA. And in contrast to other concepts like CO2 usage or disposal concepts, carbon avoidance is, in our opinion, the preferred concept in the future and also the preferred concept of any waste management.
Is the green hydrogen there? Is it ready? And I'm actually not the business developer of our company. So for me, you will also hear the challenges, whereas the business developer probably would have said, yes, we are ready. I will give a bit more context that there are certain challenges we are still facing. One thing is about safety. If we now build an electrolyzer facility, we have different safety standards than we did in the 20th century. And electrolyzer facility, it doesn't sound that dangerous, but you're producing hydrogen and oxygen. It's only separated by a thin membrane. And if somehow that membrane breaks, or there are certain other scenarios, then potentially hydrogen and oxygen can mix. And actually the picture you see here on the right is of an electrolyzer that exploded in 1975. Aspect is flexibility. As said, these older plants, they were all based on hydropower. So that was base load. can basically continuously run through the year. For the newer plants, for the plants that we will build now, of course, we could build them based on nuclear power, then this would be less of an issue. But I think most plants are currently based on building the electrolyzer based on wind or solar power. And then, yeah, in the night, the sun does not shine, so the electrolyzer needs to be shut down. You can think of adding a battery, but in principle, you will need to operate at a much lower load. It's not so much about the ramp speed. It's really about operating at very low load that can lead to gas purity issues because you have some diffusion of hydrogen to the diaphragm. And what is also a challenge is that it can mean that you need to shut down your electrolyzer. And from the chlor-alkali, from our experience in chlor-alkali, we always say the last thing we want to do with an electrolyzer is shut it down. Because if you shut it down, we get all kinds of undesirable processes in the electrolyzer. So these are things which we need to take into account in the electrolyzer design, and which suppliers, as said, we don't make our own electrolyzers, but these are topics we are discussing with the suppliers. How are you addressing this, and are you sure that your electrolyzer will work for at least 5 years, or preferably 10 years, at a good efficiency? And at the moment, suppliers in the field still are struggling to be able to show this, just because they don't have these demonstration projects running for. Is that currently, especially given by public reports on the costs of green hydrogen, that these are typically underestimated.
So we have concentration in raw material, and there are global supply chains for those raw materials. You know, over 80% of coal is mined in just 4 countries. Over 80% of iron ore is coming from only 5 countries in the world. So it's a lot of concentration which is there right now for raw materials. But tomorrow, when you're talking about hydrogen and green electricity, which are not going to have the same amount of concentration. There will be much more local production. There will be even possibly different suppliers. So, you know, today you have not only a concentration in geography, but as well concentration in companies of raw materials. So you have a few suppliers of coal, and, you know, almost everybody is buying from them. You have similar pricing, you have similar dynamics, contracts, contract period. But tomorrow that's going to change. You could be buying hydrogen from HyCC, you could be buying hydrogen from WIF, it could be from anybody else as well. And at this stage, it appears there would not be a national market for hydrogen. You know, it's not going to be like coal, where it's defined, prices are known, everybody is buying similar, but tomorrow it's not going to be the same. So your cost structure is going to change.
We need, let me say, a clear defined certificate what is green steel or what is green at the end, because everybody is doing his own calculation. So we call it greenwashing, sometimes with crazy results that companies are green. They've never been green before. So it's just a matter of greenwashing. So we need a clear standard or certificates like the CE certification in Europe to say, okay, with this standard, you can consider your product or your process as green. And then it's clear for everybody and also for the final user or customer, when he takes a decision, he buys this goods or this application, what is green and what is not. And this is what I think is very important for Germany, but also for Europe at the end.
We kind of need to train the government to give them the knowledge to be able to judge, or when we ask for subsidy for a project. We also need to learn that because, well, I'm from the chemical industry. It's quite close. As soon as we talk €1 as cost, then normally we want an NDA. So also we need to be more open to public stakeholders so that they can make the right judgment. I mentioned that the prices in public reports are just too low. They are not realistic. That's why we participated in some public initiatives to get good prices into the public domain. So it's not, we should not just blame the government for being ignorant. We also need to look at ourselves and put the right information out there.
I think what we encourage people to do is to look at their own integrated energy planning, and we let obviously countries, we support countries in making their own decisions based on their strategic needs. The technical feasibility of 100% renewables is still to be demonstrated, and also the cost of such a solution. Obviously, you have to have interseasonal storage, which might not be anything easy to do. And when in fact you look at integrated energy planning and minimum cost systems, if you run those type of simulation in a quantitative way, you find that usually there's a mix of various technologies that come out as the minimum mix. It's not one single technology like wind or solar taking the whole stage. You have a bunch of technologies, including storage, including solar, including wind, and including also nuclear, and perhaps gas with carbon capture and sequestration in order to reach your minimum cost, and also in order to provide the necessary inertia and other technical considerations. So it's up to the governments, of course, to make the decision, but it's also up to other stakeholders like the industry that needs large-scale power. To encourage governments to make a decision that's in the best interest of the industry.
We have seen how volatile is the scrap price in different markets, or even the pure availability of the scrap. So what you have to have, or when you're going to make such a big investment in a new technology or process route, what you need is flexibility, that you can easily adjust based on the market prices for raw materials, for energy. You can easily adjust with your process in order to keep your OPEX in a certain range. So, and this is, let me say, not driven by the fact it's a circular furnace or it's a rectangular furnace. Here the question is how the whole process chain and the different technologies work and deal with each other. And here I think the advantage is that we have everything in one hand.